Let's resume, I guess. Welcome back and thanks for coming to the last part of this tutorial. I want to start, or let me say we've seen now in part 1 the definition and some uses of better-quasi-orderings. We've seen in part 2 some basic facts from ordinal analysis, well, some slightly more advanced results as well. And now I want to show how they come together to produce a result on the reverse mathematics of better-quasi-orderings. I want to start with a small lemma that is not on the slides. This is for well-quasi-orderings rather than better-quasi-orderings. It's essentially the same. The lemma says if Q is a well-quasi-ordering and you have an order-reflecting function f from some other order p into q, and this other order is also well-quasi-ordering. And it's quite simple, but I just want to show it quickly. So to show that P is a well-quasi-ordering, we have to consider infinite sequences in P. And we have to show that one of these elements in the sequence is bounded by some later. Now we have a function from P to Q, so let's just push the sequence into Q. So f of x1, 0, f of x1, and so on will form a sequence in Q. But now we have assumed that Q is a well-quasi-ordering, so we find indices I smaller than j such that f of xi is bounded in Q by f of xj. That's the definition of well-quasi-ordering. And now it was assumed that this f is order reflecting, and order reflecting means exactly that, that if you have an inequality between values, then that transfers back to the arguments. So then this is very small. But I'm writing xi is then smaller in P than xj due to f being order reflecting, and that's precisely what we needed to show in order to see that P is also. I just want to emphasize that it's order reflecting maps that we need to look at. Want to see that certain things are well-quasi-ordered. And this is what's going to come up on the next slide. So there's this lemma due to Alberto Marcone, which shows that there are certain order-reflecting maps. And why are we interested in these? Well, we have just seen in this part in ordinal analysis that these orders omega to the alpha are connected to arithmetical comprehension. So if we can say something about these orders, then we may get a reverse mathematics result involving comprehension. This lemma by Marcone says that this order omega to the alpha can be embedded into the power set of the product of omega and alpha. And the product is ordered component-wise. So a pair is below another pair if the first component is below the first component and the second component. And the power set operation we saw in the first part on better-quasi-orderings, but it will also be recalled as part of the proof. So then this involves this product operation, and it turns out that this product operation can itself be bounded in a certain sense by the power set applied to a sum operation. And this is an incomparable sum, right? So elements of the sum are either elements of omega or elements of alpha, and something from omega is incomparable to anything from alpha. Internally, they are. So let's prove these things before we think about applying them. Let's maybe prove B first. So we want to go from the product. Let's consider some element in the product. This will be a pair of some n and some beta. And we want to map that into the power set of the disjoint sum. So we just map it to the set that contains n and beta. And let me maybe write it as 0, n, and 1 beta. So these are both in the disjoint sum. And the 0 and 1 just indicate which. The n comes from the omega sum, and then the beta comes from the alpha sum, and that's why they have 0 and 1. Now the claim is that this map is order reflecting. So let's consider two values. So let's assume that this value that we have given here, 0, n, 1 beta, is bounded in this power set order, which was denoted by for all exists, by another value, 0, n prime, and 1 beta prime. Now we have to recall how this ordering was defined. The definition was that each element in here needs to be bounded by one element on the right. So that means, for example, for this first element here, that 0, n, either it's bounded by 0, n prime, or it's bounded by 1 beta prime, by one element on the right. But then we have said that in this disjoint sum, the two orders are incomparable, so there can never be any in comparison like this. So it must be this first here, and that just means that in the original order omega, n is bounded by n prime. And similarly, this here must also be bounded by one of these. It cannot be bounded by this one because the two summands are incomparable. So beta must be below beta prime. And if n is below n prime and beta is below beta prime, this means precisely that the pair n beta is in the product order below the pair n prime beta prime omega product alpha. That shows that it's order reflecting the values were assumed to satisfy this inequality, and then the arguments are either pairs. This part B, apart from remembering the definitions, not too much is happening. But part A is more interesting. We also say that Andreas Weimann, you have of course proved many results of this type and much more complicated results than this. Put Alberto Marcone's name here because I know this particular result from him, but you've looked, for example, at the multiset and many more complicated constructions, and of course there are similar ideas involved. But let's now look at A. So we want to map an element of omega to the alpha, and this has the form omega to the alpha 1 plus other exponents plus omega to the alpha n, so one of these formal Cantor-normal forms. So what do we map it to? Well, the idea is that we take the pairs of the index I and the corresponding exponent alpha I. Quite straightforward as well. For all the i's, from I to n. So for each index we have a pair, which is an element of the product, and then we put these finitely many things into a set, and then we end up the finite power set. Now, why is that order reflecting? Well, let's maybe consider a second one. So beta 1 till beta n, beta m, and then that's mapped to a set of pairs j, beta j, with j ranging from I to m. And now we want to assume that there's an inequality between the values. So we want to assume that this first value is below the second value. And then we need to show that we get an inequality between these two Cantor normal forms. Okay, so what can we do? Well, this order tells us for each thing here, there's a dominating thing in here. So for each I from 1 to n, we find j from 1 to m such that from here I alpha I is dominated by one of these pairs, j beta j. And what that means, according to the order that we put on the product, is, first of all, that I is bounded by j. And I want to note, in particular, that for I, so this was each I from 1 to n, so we could have taken I to be n, and then this would give us that n is bounded by one of the j's, so in particular it must be bounded by the m. So that's one thing that I want to note on the side, that we also get this out of it. Okay, but let's get back to this particular pair. I is bounded by j, and also alpha I is bounded by beta j. Now, I and j can be different, but recall that in these Cantor normal forms, the exponents were weakly decreasing. And so if the j is bigger than I, this beta j is a later exponent than beta I, and if they were decreasing, then it must be bounded by this earlier exponent. This also comes from I bounded by j, because the exponents in the Cantor normal. Yeah, and I claim that from this, it already follows that we have the desired reflection to the arguments. So the Cantor normal forms with the alpha exponents is bounded by the Cantor normal form with the beta exponents, because these Cantor normal forms were compared in the lexicographic order, and if each alpha I is bounded by beta j, and also the first thing is at most as long as the second thing, then you just have that. So that's this lemma. And now I claim that this has the following corollary. Over RCA naught, if disjoint sums of well orders are bqo, then we have arithmetical comprehension. And in particular, in part 1, we had this result that well orders are always better-quasi-orders. That was easy to see. RCA naught can do that. So in particular, over RCA naught, if better-quasi-orders are closed under disjoint sums, then you already have. And how does that work? Why does that follow? Well, omega and alpha, they are well orders. So the disjoint sum, omega plus alpha, is supposed to be a better-quasi-order. But then this power set operation preserves better-quasi-orders. And RCA0 knows that. Because in the first part, when we looked at the power set operation, we didn't quite look at closure of bqos, but something quite similar. This was just unraveling definitions. Nothing happened there. Right? So RCA naught knows that the power set operation preserves. Even though it does not know that disjoint sums power set operation somehow. That's just the definition of better-quasi-ordering. Right? So then we know in RC0 that now this power set of omega plus alpha is a better-quasi-order, but then we know that the product is a better-quasi-order, so we know that its power set is a better-quasi-order, so we know that omega to the alpha is a better-quasi-order, in particular well-founded, and then by the result at the end of the ordinal analysis part, that was arithmetical. So not that much happened. I mean, the ingredients of this particular corollary are still easy enough, but we have already. So let's try and push that further and look at this specific order, this anti-chain with 3 elements, which I denote by 3 with an overline. And maybe the first thing to recall is that the notion of better-quasi-order was pi12, was pi12 complete, in fact. And so even for a single fixed order, saying that that is a better-quasi-order is a pi12 statement, and so it could be equivalent to one of the. That's not the case if you speak about well orders, saying that some individual structure is a well order is pi11, and so can be unprovable in strong theories, but it cannot be equivalent to one of each. But for better-quasi-orders, there's a chance that even saying the anti-chain with 3 elements is a better-quasi-order. Now, how do we get strength out of this? So when I thought about this, I suddenly thought of a sentence that you hear all the time in connection with better-quasi-orders. And I said this sentence in the first lecture, I think. Better-quasi-orders have good closure properties under infinitary operations. So, well, even if you just start with 3 elements, if you close under some infinity operation, you can get something infinite out of that. And then you have something that you can maybe work with by other methods. So let's do that. Let's apply some infinity operation to the anti-chain with 3 elements, namely this H operation. So H was the set-theoretic universe over 3 incomparable Ur elements, or maybe just the hereditarily countable sets over 3 Ur elements. And yeah, what do I want to do? Well, on the previous slide, I saw that somehow having disjoint sums of well orders would be nice. So let's try to take a disjoint sum of well orders, and we might as well just take 2 copies of the same well order alpha, because with 2 well orders we can take the larger one and form the disjoint sum of that with itself. And let's try and embed that into this structure, into the set-theoretic universe over 3 Ur elements. And the idea is, again, simple enough. We just form 2 copies of the von Neumann ordinals. Hope that these are going to be incomparable, as they should be in this sum. And in the first copy, we always throw in the Ur elements 0 and 1. And in the second copy, we always throw in 1 and 2. And otherwise, we just do the von Neumann ordinals, right? So recursively, we can assume that for every gamma smaller than alpha, we have already defined some gamma dot and gamma dot dot in the structure in our 2 incomparable von Neumann ordinals, and then we throw these together, and for safety, just put the 2 Ur elements in as well, and then let's hope that we have 2 independent copies. And this is going to work, and I will not show you the verification that these are indeed a copy of this sum here, but you can check that out. What I want to explain is why we need 3 Ur elements, and why we need to throw 2 of them into each copy. And the point is and we must use 3 OR elements, right? Because in the first lecture, we also saw that the order with just 2 elements is easily a better quasi-order. So somehow only from 3 elements it can get strong, and so there must be a reason why we need all 3 of them. And the crucial point is that if you have some set that uses exactly 1 OR element, then this set will be equivalent to that OR element in the order. So the structure of the set doesn't do anything. So what that means is, well, first of all, the OR element is bounded by the set. That's maybe not too surprising if it occurs in the set. But then secondly, also it turns out that the set is in this order bounded by the OR element. You can easily verify by induction of the rank of that. Right. And so if you build the hereditarily countable sets over 2 incomparable OR elements, then this will look as follows. So you will have things that are order equivalent to one of the 2 OR elements. And then below this, you have all the sets that don't involve any of the OR elements. So these are the pure sets, the sets without OR elements. And these are just ordered by rank. You can also check. This is a linear order, it just corresponds to the rank of these. And then above that, you will have the sets that use both OR elements. These are also essentially ordered by rank, except that well, things that use 1 OR element only correspond to that OR element, so you cut them down to this OR element, and then you compute the rank. So H of 2 looks like this, and you don't have 2 incomparable copies of the von Neumann ordinals. It's essentially linear, except that you have these 2. So that's why you need another OR element, and it turns out that it's okay if these 2 copies share one of the OR elements in there. Maybe as a quick side remark, in the first part, I implicitly used the fact that if the 3-element anti-chain is a better quasi-order, then any finite order is a better quasi-order, even over weak theories, because I internalized the quantification. And that comes from this lemma here as well, essentially, because if I have the 3-element anti-chain, then I have 2 copies of the von Neumann ordinals. Let me just draw them very small. But then what I can do is I can now form sets that contain stuff from here. So I could form one set that contains a high element from the first copy and a low element from the second copy, and then maybe another set that contains a medium element from both copies, and another one that contains a low element from that copy and a high element from that copy. And I can produce as many of these sets, any finite number of these sets that I like, and they will all be incomparable, right? Because on this copy, it looks like one set is bigger, and on the other copy, it looks like the other set is bigger, so they are incomparable. So in this way, I can produce anti-chains of any size. 3-element anti-chains. That's just a slide. Yeah, okay. So now the lemma looks good. We wanted, for the previous slide, to get at least arithmetical comprehension. We wanted to have disjoint sums of well orders. The lemma suggests that maybe we can do that if we have just a 3-element anti-chain. But there is a catch. So what I would like to reach is this proposition here over RC0. If 3-element antichain is a better quasi-order, and so are disjoint sums of well orders. But the catch is, in the first part, we saw that forming these hereditarily countable sets in general requires ATR naught. Can't do that over my. And these von Neumann ordinals, they are indeed infinite, so it's not enough to check just the finite. I really need this infinite structure, and then I need ATR naught. So how can I get around that? Let me maybe clean the blackboard again. So the point is that if some set A is not bounded by some set B in this set theoretic universe with Ur elements, then that means, equivalent to, there exists some element of A such that for all y in B, X is not bounded. Okay? And the problem is that for the infinite sets, I cannot check these inequalities. And in particular, I cannot find the correct X. And that's what I need ATR naught for in general. With ATR naught, I can well, build a set of indices of trees that can be embedded. And so if I have ATR naught, then I can really build a set of all pairs which I have this inequality, and then I can maybe search for the right X. And without ATR naught, I cannot do this. And now the way around this is that in the end, for this proposition, I'm not really interested in the full structure. I'm just interested in the 2 copies of the von Neumann ordinals, or maybe in their transitive closure, something like that, in order to make sure that everything works out well. And on this much simpler structure, the transitive closure of my 2 copies of the von Neumann ordinals, I can effectivize the construction by introducing something like a notation system. And I think this is also a point where maybe helps a little bit to be a proof theorist. And it's not necessary to know proof theory for this, and other people would have had the idea as well. But as a proof theorist, I like this fact that we have some infinite structure, but still I can build a notation system that allows me to work effectively with the part of the structure that I actually need. Let's maybe briefly look at how you do this. I don't have time for everything, so let me just check what I wanted to say. Let's consider the term system. And now call transitive closure of A plus A. And it just consists of all these von Neumann ordinals from the 2 copies, together with the things in their transitive closure, which is the Ur elements themselves. So this will be 3 together with all the alpha dots. Let's call them gamma dots. Together with the gamma double dots. And I just consider these as terms. They are very simple terms. Alpha is a fixed order, and I just consider this stuff. This I can do in RC and all that. There's no construction going on. And now I'm going to take inspiration from this embedding as sets, but I don't take these sets to be something official. But now I still have to say, in some sense, what the elements of these terms are. So let's just define it. What are the elements of some gamma prime? Let's just look at what they would be in this set theoretic construction. They would be the U elements 0 and 1. And then also all the delta dots for delta below gamma. And similar for the double dot, gamma dot dot, the elements are these two U elements, all the smaller double dots. And then I can say what are the elements of an U element. Probably the canonical choice would be they have no U elements, they are empty. But we saw earlier that in the definition of the order on these sets, it's convenient to identify an U element with its singleton set. And now I'm just defining some E. It's not really the set membership relation, I'm just define something. So I might as well say that the elements of an U element are I. And then I have the following lemma. Maybe I should put it there. Now this is a lemma over RCA naught, saying that there is a function R taking two elements of this term system and mapping it to another one. Such that if X is not below Y, then this R function applied to X and Y picks me something that belongs to the elements of X and is not bounded by anything from the elements of Y. I didn't tell you what this order is, the order on a term system, but it's just what you expect. The dots are incomparable to the double dots. The U elements lie below the things that. And the point of this lemma is this is exactly what I said earlier that I cannot do effectively on the real set theoretic structure. If I have a failure of such an inequality, there should be something in X which is not below anything in Y, but I cannot pick this thing effectively. Not. But in these notations, I can do it. How can I do it? You can just write the function R down. So let's maybe write down one or two examples. So for example, what is R of alpha dot and beta dot? And I'm only really interested in this when alpha dot is not below beta dot, because this is the only case where if this happens, then I have some conclusion, otherwise I don't care what is being picked. And what that means is that alpha is not bounded by beta. You can leave the dots away, so that alpha is larger than beta. And what do I pick? Well, I just pick beta dot. And the point is that beta dot is indeed an element of alpha dot according to this E function, because according to this E function, alpha dot contains all the smaller dots, and beta is one of the smaller dots. But also, this beta dot is not below anything in the elements of beta dot, because the elements of beta dots are all smaller dots. And maybe just one second example. So if you have things from the two copies, maybe some alpha dot and some beta dot dot, they are never comparable. So I always have this case where I need to do something, the case that I'm interested in. So what can we pick? I need to put something that's in the elements of alpha dot, but somehow not really comparable with the double dots. I can just pick the Ur element 0. That's in all the dots. But it's not comparable, so the elements of the double dots is not comparable with the Ur elements 1 and 2, and also it's not comparable with the double dots because none of these. And I can do the same in all cases. In the end, it's really quite simple, but somehow I really like it, maybe also because I wouldn't have written it down without knowing what the set theoretic structure looks like. But then in the end, it's just an extreme. Okay. Now we have resolved this problem. We cannot handle a full set theoretic structure over RCA0, but we can still mimic this argument, and then we learn that over RCA0, if the three-element antichain is BQ, then also disjoint sums of well orders are BQ. But then we know from the previous slide, if disjoint sums of well orders are BQ, then we have AC0. So altogether, over RCA0, if the three-element antichain is BQ, then we have at least AC. And that's already something, because we saw that for the two-element antichain, there's this elementary combinatorial argument, and now apparently for the three-element antichain, that cannot be as elementary. Now we'll try to improve a little bit on that, and that's already the last slide. So you can do a bit more, namely rather than just embedding these notation systems omega to the alpha, you can even embed these notation systems epsilon alpha into, now you just take the hereditarily finite sets over these words. So for the Ur elements, so you're given some order alpha, then you make it a little bit bigger. This is just the usual operations of ordinal arithmetic, so this is still a linear order, and then you add one incomparable element. So you have to have some incomparability, because otherwise this H operation doesn't do anything. So you just add one incomparable element, and then you still form the sets, but in this case you only form the hereditarily finite sets. And these are easily handled in RCA0. So here you don't need to do any tricks via term systems, because that is finite version of this construction that can really be proved. Yeah, and this proposition is that there is an order reflecting map from epsilon alpha into the structure here. And also it turns out that epsilon alpha is essentially as large as possible here. Somehow these hereditary finite sets, they don't do much more than the epsilon number, and I think that you have much more precise bounds of these types. I just did the order reflecting map and checked that I couldn't prove it much, but you did much more things, I guess. Okay, but what we then learn is that if the 3-element antichain is bqo, then first of all, 2 copies of this well order are bqo. So in particular, if you just keep 1 copy and shrink the other copy to 1 incomparable element, then this is still bqo. This operation preserves bqos over RC0, so you know that this whole thing is bqo, and then you learn that this order epsilon alpha that admits this order map into it is a well order. So then you know over RC0 that if 3 is bqo, this thing is a well order. And then we saw in the part on ordinal analysis that this is. Then you learn that from finite better-quasi-orders. And then also in the first part, I mentioned this notion of delta 02 better-quasi-order. So better-quasi-orders could be defined via continuous functions, and if you relax that a little bit and admit delta 02 functions, then you get a notion that is equivalent over strong systems, but not necessarily over weak systems. And that played a very important role in Antonio Montalban's analysis of Fraïssé's conjecture. And now also over RCA0, if you know that the 3-element antichain is even delta 02 bqo, then I know how to reach arithmetic. Yeah, and so how can we improve on that? So David Manca showed that this first part of the theorem is not an equivalence. So ACA0 plus does not prove that 3 is bqo. It must be strictly stronger. And what he did was essentially iterate this HF construction. If we can briefly mention, you could think if you form all the hereditarily finite sets over something, and then take that as input and form the hereditarily finite sets again, nothing happens because you're already closed under taking finite subsets. But actually the order will change, because after the first step, you treat all these hereditarily finite sets as elements for the second step, and that makes a difference whether you treat something as an element. And then you can iterate this construction, and it's very technical to iterate that over weak base theory, but that's what David did. And then from this iteration, you learn that you get well-foundedness even for the first fixed point of the epsilon function. And I think that that result is significant because, of course, we wonder what is the real strength of 3 being bqo. And I mean, if it's not ACA0 plus, then, well, there's one good candidate eliminated. And so the final question is, well, how strong is this really? And I think the conjecture is that 3 being a better-quasi-order is equivalent to ATR0. And the slides say that Fyodor Parkhomov has a sketch of a proof showing that. And I should add, I think that other people from the Gantt group are involved in that as well. So, Alak, I know that you have done relevant work on that, and Philip Provenzano, you have done relevant work on that, and maybe other people from the Gantt group as well. But, well, I know about this from Fyodor, and I wrote him an email last week asking about the status of this. And he gave a talk about it at some point, but he wrote that it's not recorded, and there's no written record of the proof that's publicly available so far. So I just cannot say more about it. I mean, it's a bit an anticlimax to my tutorial, but I can just say that there might be this result coming out of Gentzen, and let's look forward to it. So yeah, it might be that this is equivalent to ATR0 after all, which would mean that, I mean, the sort of easy way to show that this is bqo is using the open Ramsey theorem. And I said earlier that this might have been excessive, but maybe it's not after all. Maybe this is really this one. So then, just for final reading, And this first thing is the paper that contains all the details on what I said. And that's really the only reference for the third part, but I put some more just so that you could read more on better-quasi-orders if you were interested. So that's the paper that I mentioned earlier, that this minimal bad array lemma is equivalent to pi-1-2 comprehension. Then we have a paper with Alberto Marcone about a full classification of finite better-quasi-orderings that are provable bqos in weak systems. And then I wanted to mention, just because it's I think the most recent paper that I saw coming out on this type of topic, a paper by Fyodor Parkhomov and Giovanni Salgado on Nash-Williams theorem about the ranges about sequences with finite range. Interesting well-quasi-order closely related to better-quasi-orders. Yeah, so I think that's all I have to say, and I'm very happy to